Welcome to Advanced Group Theory. Today, we are going to explore the fascinating applications of Sylow's theorem. Imagine you are a detective trying to figure out if a large, complex organization has a secret, independent inner committee that controls things behind the scenes. In mathematics, this organization is our group, and that secret committee is called a normal subgroup. Let us dive in and see how Sylow's theorems act as our ultimate magnifying glass. Now that we have our detective analogy, let us define our terms formally. Why does this matter? Because proving whether a group is simple or not is one of the biggest challenges in abstract algebra. A simple group is like an indivisible atom. It has no proper non-trivial normal subgroups. A normal subgroup is a smaller group inside the main one that remains perfectly balanced, no matter how you mix it with outside elements. Sylow's theorems give us a way to count specific subgroups based purely on the total number of members in the group. If we can prove there is exactly one such committee of a certain size, it is forced to be a normal subgroup, meaning the group is not simple. Before we can count these subgroups, we need to understand the size of our group. This formula shows where our investigation begins conceptually. We take the total number of elements in the group, denoted by the absolute value of G, and break it down into prime components. Here, P is a prime number, and K is the highest power of that prime that divides the group's order. The variable M represents the leftover part of the group size that is not divisible by P. As the size of the group increases, finding these prime factors becomes the crucial first step. If P increases, the remaining factor M must decrease for a fixed group size. With our group factored, this brings us to the core mathematical rules we will use. The third Sylow theorem gives us two strict conditions to find NP, which is the total number of Sylow P subgroups. Conceptually, this theorem restricts the possible number of these subgroups. The first rule states that NP is congruent to 1 modulo P. In plain English, if you divide the number of subgroups by the prime P, the remainder must be exactly 1. This severely restricts the possible values for NP, forcing it to be a number like 1, P plus 1, and so on. Following the first rule, we have a second condition from the third Sylow theorem. This formula tells us that the number of Sylow subgroups, NP, must perfectly divide the leftover part of the group size, M. The vertical bar simply means it divides evenly without any remainder. When we combine this rule with the previous remainder rule, we often find that the only number satisfying both conditions is 1. When NP is exactly 1, it means there is only one subgroup of that size, making it unique and therefore a normal subgroup. Now that we have our formulas, let us see this with a concrete example. We are given a group with exactly 15 elements, and we are asked to prove that it is not a simple group. To do this, we need to show it has at least one normal subgroup. Why choose this approach? Because the third Sylow theorem is perfectly designed for this. We start by writing down the order of the group, which is 15, and breaking it into its prime factors, 3 and 5. As a general rule of thumb, we focus on the larger prime first, which is 5, because larger primes usually have fewer divisors, making our math much easier. Continuing with our prime 5, we apply the first rule of the third Sylow theorem. We know that the number of Sylow 5 subgroups, N5, must leave a remainder of 1 when divided by 5. This means the possible candidates for N5 are 1, 6, 11, 16, and so forth. Next, we apply the second rule. The number N5 must also perfectly divide the remaining part of the group size. Looking back at our factorization, the remaining part M is 3. So N5 must divide 3 without any remainder. Let us finish this example by finding the intersection of our rules. The only positive numbers that divide 3 are 1 and 3. Now we compare our two lists of possibilities. We need a number that is in the first list, meaning it leaves a remainder of 1 when divided by 5, and is also in the second list, meaning it divides 3. The only number that satisfies both conditions is 1. Because N5 is exactly 1, there is a unique Sylow 5 subgroup. Physically, this means this subgroup sits alone and perfectly balanced within the group, guaranteeing it is a normal subgroup. Therefore, the group cannot be simple. Having successfully analyzed a group of order 15, let us tackle a slightly different problem: analyzing a group with 33 elements. This is a classic example of a group of order p times q, where p and q are distinct prime numbers. We want to find out if this group has any normal subgroups. Our approach remains exactly the same. We start by factoring the total number of elements. 33 breaks down neatly into the prime numbers 3 and 11. Following our rule of thumb, we will begin our investigation by looking for Sylow 11 subgroups, since 11 is the larger prime. Moving forward with our prime of 11, we apply the first rule. The number of Sylow 11 subgroups, N11, must leave a remainder of 1 when divided by 11. This gives us our first set of constraints. The possible values are 1, 12, 23, and so on. Next, we apply the second rule. The number N11 must also evenly divide the remaining factor of the group size. Since we factored 33 into 3 times 11, our remaining factor is 3. Therefore, N11 must be a divisor of 3. Now we bring it all together for our final result. The only positive divisors of 3 are 1 and 3. We now have our second set of constraints and are ready to find the intersection of the two rules. Comparing the two conditions, we look for a number that is a divisor of 3 and also leaves a remainder of 1 when divided by 11. The only number that fits perfectly is 1. Therefore, there is exactly one Sylow 11 subgroup. Because it is unique, it acts as a foundational building block and is a normal subgroup. This proves that a group of order 33 is not simple. To truly understand what we just calculated, let us look at this visual representation. The large outer circle represents our entire finite group G. On the left, you see a single blue circle labeled P. This represents the unique Sylow P subgroup we found in our examples. Because there is only one, it sits uniquely and symmetrically in the group, acting as a normal subgroup. On the right, you see multiple orange circles labeled Q1, Q2, and Q3. When the math allows for multiple subgroups of the same size, they are not unique and therefore they are not normal. This diagram perfectly captures the physical interpretation of Sylow's counting rules. Now that we have seen the math and the visuals, you might wonder why this matters in the real world. Classifying finite simple groups is monumental. It is literally like finding the periodic table of elements for mathematics. Sylow's theorems act as the chemical tests that tell us whether a complex molecule, a group, can be broken down into smaller atoms, which are the simple groups. In fields like cryptography and coding theory, understanding the structure of these groups is absolutely vital. It helps in designing secure encryption algorithms. If a group can be broken down easily, it might be vulnerable to mathematical attacks. So cryptographers rely on these theorems to choose the safest structures. Let us wrap up what we have learned today. We saw that the applications of Sylow's theorem provide a powerful, systematic way to uncover the hidden structure of finite groups. By simply analyzing the prime factorization of the group's total size, we can determine how many subgroups of a specific prime power size exist. When the mathematical rules restrict this number to exactly 1, we guarantee the existence of a normal subgroup, proving the group is not simple. You have now mastered an elegant counting method that remains the absolute cornerstone of classifying all finite groups in abstract algebra. Great job!